Good afternoon, everybody. This is Steve Wilson from the State Water Survey and manager of wateroperator.org. Welcome to our webinar today on groundwater and well care. This is the second time we provided this webinar. We did it also in April. And so the core content here is the same as it was in April. The questions, though, at the end are certainly all different. So keep that in mind. Okay, so a little bit about today's webinar. It's not really pre-approved for CEU credit unless you have been informed by your state that it is. I know for the April webinar, it was approved for CEUs in Louisiana, but we will provide certificates. And for those of you who can work with your certification body in your state or your primacy agency to get certification credit, we will provide that information. You just need to email us at info@wateroperator.org. We are recording this, and it'll be available both on our events page at wateroperator.org and on our YouTube channel. So you can look for us at either of those places. It'll be there in a few days, probably by early next week. We do have several folks on the line for our staff who will take your questions in the question box or the chat box. And so if you have questions, what we're doing is we're keeping a list of those during the webinar today. And at the end, when I get to the last slide, we're sharing a Google Doc that'll have all those questions on it, and we'll pull those up and we'll stay around and answer questions as long as you have them. So the last thing to note is we are still at home. I work at the University of Illinois, and we're home through the end of the year. And so I have a daughter who's a fourth grader in school. Sometimes our internet might decide to have fun with us. And also things like my neighbors deciding to mow their yard. So you just never know what you might get today. Hopefully none of those things are a distraction, but I just want to point it out in advance in case something comes up. So again, I'm Steve Wilson. I'm a groundwater hydrologist at the State Water Survey. I'm in the groundwater section. And with me is Jennifer Wilson, who's our communications lead for wateroperator.org. And she's taking our questions today, as well as Dick Meiliger, who's vice president of municipal well and pump. He was also our guest for April webinar, and you know, having someone who's out there putting municipal wells in, dealing with that day to day and all the issues on maintenance and everything else has really helped us. And he's answered all the questions really for today that we'll have at the end. And he's also been a huge help to me on advice and other things about our program and on these type of issues related to groundwater and wells. So it's great to have Dick involved, and we really appreciate his time and helping us out. So a little bit about the water survey. For those of you not in Illinois, Illinois has, in addition to our state geological survey and natural history survey, we have a sister agency. It's the state water survey. There's one more in the country in Oklahoma, but they've only started a number of years, not very many years ago. And the water survey in Illinois has been around since 1895. It was started because of public health issues, mainly cholera and typhoid. And so our first job was to document the water quality of community water supplies in the state. And so there's a lot of cool information in our historic logs and data about every community in Illinois. And in some of those, we have records going back at least to 1895, if not before. Just as a quick example, this is Pana, Illinois, and it was an investigation the water survey did after they had a typhoid outbreak in April and May of 1916, excuse me. And our job was to go in and figure out what the source was. The town had a public water supply, and they just built a new treatment plant in 1913, but it was expensive to run, so the mayor wouldn't let them use it. They also had half the town sewered and the other half wasn't. And so I know we went in assuming that one of those things was going to be the culprit, so to speak, because they weren't treating their water yet. And it turned out it was the Pana Ice Cream Company, which was also the milk seller in town. So what ended up happening is they had one large vat or container that 7 different farmers brought their milk in and combined. And then anyone who wanted milk went over to that container and used a bucket to scoop out their milk they were going to take home. And that was the source. And so there's a lot of documentation that goes along with this map, but you know, it's pretty cool to read through this stuff and see what was going on back then and how, you know, the water treatment world was evolving. We still have some of those issues today, right? I mean, sometimes village board or town board or mayor or water board may decide to make a decision that's based on dollars and not necessarily what's in the best interest of the folks in the community. Luckily, that doesn't happen very often, but we still certainly see cases of that. Just a couple more pictures from our files. This is a pump test using an orifice bucket. We have a number of these. We still have one that we use today, and we have drillers borrow them once in a while from us. And also just think about, if you're familiar with well drilling, this is a well that was put in on the U of I campus in 1926, I believe. And if you look at the work that went into not just the spacers, but riveting every 10-foot section of that pipe, it was quite a job. And so, today's modern drilling methods and the way we've come along has really changed the world, so to speak. But a lot went into it back in the day. So a little bit about the water survey. I'm in the groundwater science section. We not only house the state's well logs, but we provide, we do data collection through that. We also have a water quality lab, but we do research and public service. And this is just a pump test at the city of Chillicothe that we were involved in, using an orifice tube there to pump that well and conduct an aquifer test. But we also monitor stream flow. We have recorders. This is an old Stevens recorder. Most of our monitoring wells around the state now, our observation well network, is actually, we're using telemetry and pressure transducers, just because one, we get the data in real time, and it's allowed us to put our hydrographs online and show that information near real time. And we're working on trying to even improve those capabilities. But we also, if you're an Illinois operator, you're familiar with the Illinois Water Inventory Program. Our state Water Use Act requires every community water supply to send their water use in to us once a year. And so we have that data going back to 1978, which is really helpful whenever you're trying to plan and look at the growth of cities and things like that. As far as public service, again, we do pump tests, not as many as we used to, but we also house the well records, and we can have well design capabilities, as well as we do a lot of public outreach and education programs. We run a program called the Private Well Class. It's nationwide. It's meant to help people with private wells understand how to take care of them and what risks they have and those sorts of things. Plus, our public service lab does water quality analysis, mostly for private well owners, but we have others as well for inorganics and metals. And then on the research side, we do a lot of work looking at regional groundwater quality and availability, contamination problems, well interference. We've really lead the way in groundwater modeling. We've developed some methods that are unique. We're working now with some of the cities in the Chicago region because of the problems with the deep bedrock aquifers there, as well as looking at things like PFOA and PFOS and lead and other kinds of contaminant studies, arsenic as well. So we're going to go through a little geology lesson. What I've learned and what I assume for most water operators is you may have a well and a groundwater system, but it's just your source of water. It's not necessarily, you're not a geologist by trade, and there's just a lot of things that we all can learn from each other related to those things. So this is a porous system. When you look at a block of either rock or sand and gravel, it's either the fractures in the rock that hold the water or the space between the sand grains and the sand and gravel aquifer that hold the water. So that, how porous that unit is, again, whether it's bedrock or whether it's sand and gravel, is called porosity, and it's one of the core measures of how good an aquifer might be. So in this case, it looks like sand grains, the water travels between them. That's why sand and gravel aquifers are so productive, because the grains are large, so there's a lot of water available, as much as 30% in a completely saturated aquifer in sand and gravel. And so it's why your well is able to produce so much if that's what you're in. And as far as bedrock, it's usually fractured flow. Sandstone, if you're in a sandstone aquifer, can have some secondary porosity in the rock itself, but for anything else, limestone, dolomite, even granite, those sorts of things, it's just the fractures that provide the water. So when you drill a well into a fractured system or into a bedrock system, it really depends on what fractures you hit. If you hit a bunch of fractures, you may have a lot of water available. If you miss all the fractures, you may have hardly any. And we see that in certain places in Illinois, especially one irrigated area. You can drill a well, and if you hit one of the large fractures, you're pumping 12 to 1,500 gallons a minute for your irrigation system. If you miss, you may have a 400-foot, 12-inch bedrock well that only produces 30 to 40 gallons a minute at most. And so they're really different systems when you look at sand and gravel versus bedrock and what you need to understand. So just another look at that. The ones on the top are unconsolidated, which means sand and gravel, clay and silt. It's usually the alluvial areas, which are the bottoms along a river where sand has been deposited, as well as silt and clay, or in glacial areas in like the northern third of the country where there's glacial deposits that are still on top of bedrock, like we have in most of Illinois. And so it's an unconsolidated aquifer. It's the space between the sand and gravel grains. And it depends on how sorted that is, how well or poorly sorted, what the porosity might end up being. But in bedrock, again, you have different kinds of rocks shown here on the bottom. It depends on the size of the fractures, the interconnectedness of the fractures, and the number of fractures you hit. So, you know, like the one on the right, caverns and limestone, we have that in southern Illinois, Indiana, Kentucky, and Tennessee, as well as other areas of the country. You can hit a large cave, and that's basically just, that cave was formed by water dissolving the limestone. And so if it's full of water, that's a heck of a water supply. And if you get in things like granite, like in the Rockies, where the porosity there may be less than 1%, just because granite's very hard rock, the fractures are small, they're usually near the top, and if you don't hit very many of those, they're not that extensive and you're not going to have much water. And so it's just, again, good to know. It makes a difference, and I'll explain a little more about where your water's coming from, how close to the well you're actually getting your water from, and some of those things. The other term that's really important and related to how much water a well can pump is the permeability of the aquifer that the well is finished in. When you're in a gravel versus a silt or a clay on the left here, it's highly permeable, sand and gravel, larger grains, and allows as much as 3,000 feet of movement a day. And permeability is a measure of the velocity, but the way water moves through the ground is also based on the difference in water level. So when you're not pumping your well, it's at a static water level that's equal to the static level in the aquifer. But as soon as you turn your pump on, you're drawing down the water level in the well. That creates a cone of depression because water wants to be flat. So think about it like if I pour water on the end of a table and I lift up that end, water runs downhill. That's what it does whenever you turn on your pump as well. It runs towards your well because the pressure is lower there, and it's trying to fill that in to make the pressure equal again. Almost like if you think about your bathtub, the water surface is at the same elevation. But whenever you turn on the drain, it starts lowering on the end where the drain is, and all the water flows to it because it's trying to be level. So permeability is just how fast it can get there. You know, in a bathtub, there's no resistance because there's no grains in there. But if you put things in there, like if you put a bunch of clay or sand, you'd see a difference in how fast the water drains out. Because when you get down to really small particles like silts and clays, even though they may have the same porosity, like the clay shown here may have a porosity of near 20 or 30%, but the grains are so small that water can barely move through it. So, you know, on the low end, a really tight clay will only move, water will only move a foot every 10,000 years, which is why clays and silts, as well as on the right there, shale and rock that are cemented, are considered Aquitards or aquicludes, meaning water doesn't go through them, instead of aquifers where water can be moving through that system. So on the right side, we have limestone and sandstone. Limestone, again, it's the fractures and solution cavities that are created, like, you know, that's why caves. In some parts of the country where you have karst, where there's sinkholes and things like that, and a lot of springs. We have that in southern Illinois as well as there's a lot of other areas in the country. Water can move pretty freely through a cave-sized hole because, again, there's no resistance. So it really depends on the head difference, which is the water level difference. And then, as I mentioned before, in a sandstone, and where this, you know, sandstone is basically sand that's been cemented together and to form rock. But sometimes that cementing material can dissolve, as it says here. And so then you do have some secondary permeability or water stored in the grains of the sandstone in those cases. So there may be a little more water available in a sandstone than just what's coming through the fractures. Shale is basically cemented clay. It's really tight, bedrock formed clay. And so that's why it's 1 foot and 100,000 years on the low end, because if it's a really tight clay, water barely will move through it. So it acts as a barrier for water flow. Okay, and these are just other examples of the way water moves through. Look at this, like these are horse troughs full of that material, and you poured water uniformly across the top. This is kind of the wetting front, or how it moves through. And so you can see the sand and gravel, it kind of moves through all the grains in the sand and gravel. So it's kind of got an even front. A little bit of variability in the sand causes a little bit of differences. But then on the lower left, crystalline bedrock, you know, as I mentioned, the porosity can be less than 1%. The fractures aren't necessarily connected. And so you're really hoping that you're hitting a bunch of fractures whenever you drill into that, if that's what you have. And that's unfortunate. A lot of times in areas like that, that's why they have lakes or surface water systems, because there just isn't enough water available. There may not be any aquifer with potable water. So then dolomite, you know, it's formed in layers. And again, these are also simplifications. Rock does not lay flat in the ground. It's usually at some angle. And then every once in a while, there's some kind of geologic fracture or break where the units have separated, you know, the mountains were formed, or when there's been earthquakes. And so it's much more disjointed to this, but it's really meant to just show, like the one on the bottom, how water would move through. And so, you know, it's not uniform, it's not even. All aquifers aren't created equal, and that's why you need to understand what you have in your area and where your water supply is. This is from the Iowa Department of Natural Resources and their manual, and it's just a groundwater basics manual. This is what we see in Iowa, Illinois, glaciated areas. You know, there's glacial drift on top, and that may or may not have layers of sand. This example, really, they're very small layers of sand where the glaciers have receded or advanced and then melted, and except along the river valleys. And, you know, for instance, the Mississippi is now, say, half a mile wide in parts of Illinois. But the actual bottom ground where the Mississippi used to flow when the glaciers were melting might be 5 or 6 miles wide. And most of that bottom ground is full of sand. So you see a lot of communities that are further, you know, like here that shows 2 wells. One's in the sand and gravel at the top up there, and the middle one is down into the sandstone and limestone in the bedrock aquifer, because they're off that. The other option a community has is putting a well in the sand and gravel and alluvial bottom, like along a large river system, and then piping it back to their community. And we certainly have a lot of that in Illinois as well, in areas where once you get off the bottom ground and get up in the uplands, there may be, like in this example, that glacial drift is all clay until there's no aquifer that well penetrates. And so they went down into bedrock. As far as groundwater flow, you know, the hydrologic cycle, most of that we see is about rainfall running off into streams and then eventually the ocean and evaporating back up and starting over. Well, there's a whole groundwater component that's much more complicated that also plays a part of that. The recharge area shown on the upper left and right where water infiltrates into the ground, and then it can move either in a shallow system, it might move within days to a seep, like it shows on this diagram, or a spring, or it can move straight down through the Aquitard over time and eventually get to bedrock. And but all along here in all of this system above the Aquitard, that's above the lower aquifer, it's a shallow system that eventually runs back to that stream. And that's because the water level in the stream is lower than in any of the aquifers. And you can see the water table shown on the in the dotted line on that. But all that water is flowing, eventually discharging to the stream. And so it becomes surface water again, and you know, starts the whole process over again. But what's interesting here is an aquifer that's truly confined and deep enough may have a recharge area that's hundreds of miles away. And so even though there's a stream above it here in this example, the lower aquifer is flowing from right to left. And its discharge point, as I said, could be 100 miles away. And there is a very little bit of water moving through that Aquitard and pushing down into that aquifer. but it's not a lot. Most of the recharge is probably coming from somewhere off to the right in that system, because the Aquitard just doesn't allow that to occur. And so that's, there's really three types of aquifers, or well, there's three types of geology that determine what kind of well you have. And I included dug and bored wells here mainly for non-community systems, because sometimes, a campground or, a small business may be in an area where there's no real aquifer. And so they may have a large diameter dug or bored well, especially if it's very old, or if it's bored, if it's more modern, but it's a large diameter well meant to store water. And so I included it here. Most community water supplies aren't going to have a dug or bored well. It just doesn't provide enough water in real time to supply a community and daily use. The other types, though, are either sand and gravel aquifer wells or consolidated rock wells. And the reason we classify them that way, I know there's a lot of ways to put a well in. You can punch them in, there's a lot of other things you can do in types of drilling, but they're in one of these types of formations, and that really dictates what kind of supply you're going to have and what considerations you need to make. So, and in some cases, like we showed in our examples, there may be choices. You may have 2 or 3 aquifers that you could decide to use. In a lot of cases around a community, there's a shallower sand or a shallower aquifer that a lot of private wells are on in that area, but it doesn't supply enough water for a large community. So the community well may be much deeper in a separate aquifer where they can pump, more than a few hundred gallons a minute without having to worry about not having enough water. So as far as dug wells, we see all kinds of them, all from the old dug well that's on the upper left here that has many problems. The reason it looks muddy on the lower right is because that's a cattle pasture, and those posts are all rubbed raw from cattle rubbing and grazing. This well's only 25 feet deep or so, and it's getting water from the water table. That's a field. This year it looks like it's in set-aside ground, but it may not always be. And again, this is a pasture. Cows are defecating there and everything else. And so this is a really poor choice for a drinking water supply. And again, we wouldn't expect to see this for any regulated public water supply, non-community or community. The other 2 are also bored wells, one using concrete tile to the surface, and the lower left one with concrete tile that stops at 10 feet. But then they've covered the upper 10 feet with clay and concrete to make it less susceptible to surface contamination. And here's what those 2 look like. The one on the left has a concrete tile going over the surface. If it's done properly, it's got concrete or clay in the annulus around that 36-inch pipe or concrete tile down to at least 10 feet, and that's the law in many states. But then below that, you're taking advantage of the annulus, you're putting gravel pack in there so that you've got more storage. And that's really why you have a large diameter well, is because you need the storage. Water seeps in slowly. It doesn't, there's not necessarily any sand. This shows a thin sand lens, but it may not be that extensive. And then the diagram on the right is the same type of well, except they put a concrete pad down below 10 feet so that they can fill that upper 10 feet with material that's going to help prevent surface infiltration. Okay, so sand and gravel wells, if you're in a sand and gravel aquifer, your well has a screen. And what I want to point out here is if you have a 200-foot well that's in sand and gravel, you likely have, as a community water supply, maybe 10 to 20 feet of screen. And if your aquifer is not as good, it may be screened through the whole unit. But if you have a thick, aquifer I'm thinking about in Illinois is the Mahomet. There's places where it's nearly 200 feet thick and it's fully saturated. You probably have a 10 to 20 foot screen for your well. A 12-inch well, this may be pumping 200 or 300 gallons a minute is a typical type of system. And the deal there is, if you have a 200-foot well, you only have water entering your well in that lower 20 feet where the screen is. The rest of that casing is either PVC or steel, and it's solid. And so no water can come in your well except at the screen. And the way screens are sized is based on the sand and gravel that you have. The driller will take samples as he's drilling through the unit and then size the screen accordingly, along with a gravel pack around it that'll prevent sand from pumping through. Sometimes some fines will pump through. But again, and Dick's going to talk about this later about developing wells, probably a critical piece there to make sure that you've got everything in place and you've sized it right and all those things. This is just a example of a well in Illinois showing the log. If you don't have your log or haven't looked at the log for your well, you should get it from your state. Hopefully they have it. It's not always available. We were doing a study 20 years ago or so, working with a number of rural communities in one county, and they had had a fire a long time ago, and their records were all lost, and so they had no records on the depth of their well or any of the information about how it was constructed. But that's a rare occurrence for a community or a public water supply, and so it's got a lot of great information on it. And this was just meant to show an example of what an Illinois log looks like and the information that's available. Regarding bedrock wells, the difference here is most of the time, and not always, sometimes you're casing a lot more depending on how friable or what's in the material of the bedrock, but most bedrock wells are only cased 10 to 20 feet into the rock. You usually use steel casing, you seed it 10 to 20 feet in, and the rest of it's open hole. And the rock acts as the casing itself. When you're drilling through a solid rock, you can put a hole through it and it doesn't break apart, but you're trying to define fractures. That's where the water is flowing. And so you need to have an open hole in order to take advantage of those fractures can enter the well bore where your pump can then pump water out. And again, the difference here is a 200-foot well. It really depends on the elevation of the bedrock. If your bedrock surface, like in this case, is under the saturated overburden, if your bedrock surface is at 20 feet, you might only have 50 feet of casing. And most states have rules on minimum casing, but it didn't always used to be that way. So we see some older wells, not necessarily in Illinois, but I know in New York, I've run across bedrock wells where there's only 15 or 20 feet of casing. And even though it's a 400-foot well, it's all open. And why that's an issue and why you need to understand that is because if any of those fractures are close to the surface or they run, like the one in this example, the one running off to the upper left, if it makes it to the surface or near the surface, then it's much more susceptible to rainfall events and infiltration that then can get to your well, even though your well is considered, quote, deep. And so understanding, again, your log and how much casing you have is an issue, as well as the number of fractures and how productive your well is. Because if it's not that productive or there aren't many fractures, then it might mean that your water can be coming from further away. And that's the third bullet here, and just something to consider. Okay, this is an example of a non-community well, Camp Algonquin, Illinois. Well logs are public information in Illinois, so I show this as a great example of a bedrock well. If you look over on the right side, they show that they've got PVC from 1 to 79 feet, 179 feet, excuse me, and then black steel from 179 to 199. So if you look down at the log number 18 down there, they hit limestone at 189, okay? So they seeded this casing, the steel casing, 10 feet into the rock from 179 to 199, and the rest of that is open hole. There's no casing below it. So from 199 to 260, that's an open hole. I always point this out. It's a great example because someone made a mistake on this, probably somebody in their office for the driller. I'm sure they're used to looking at the bottom formation and assuming that's where the water's coming from. They hit 3 feet of shale at the bottom, and so they included that on the log, and they decided to stop. But the person in the office who filled this out put for number 12, water from shale from 257 to 260, which is dead wrong. They're not getting their water from the shale, they're getting it from the limestone. And so in this case, yeah, water can come in anywhere from 199 down to 260. And that's how most bedrock wells are installed. And again, sometimes you run into very friable rock, or it's sandstone that is susceptible to, during pumpage, to breaking off and getting into the pump. You may have casing most of the way down, and it may actually have cut slots in the steel casing in order to have an avenue for the water to get in. Okay, so Other things you should know, and I'm using Illinois as an example. I've worked in Illinois aquifers for 30 years. Your state will have maps of where your major sand and gravel aquifers are, where your bedrock aquifers are, water quality, a lot of different tools if you know who the right folks to ask are. Your primacy agency that you have to deal with for compliance should be able to tell you who those folks are. It may even be them. And so it's very different in every state. Your USGS, State Geological Survey, DNR, DEQ, you know, there's a lot of different names they go by depending on what their roles are and how the state set up their drinking water programs. So, but a lot of information is available through, like for us, through the water survey, we typically do regional assessments of aquifers. So this is in northwestern Illinois, where the ancient Mississippi used to run. So before Illinois was glaciated, the Mississippi actually turned and came through the center of the state. It didn't flow where it does now with the border with Iowa. But then glaciers came and turned the flow of the Mississippi to where it is today. But those ancestral valleys are all full of sand. And so a lot of sand in some cases. And that's what the Muhammad is, I mentioned earlier. It's an old bedrock, it's a bedrock valley where a river used to flow, the Muhammad Tays. And you know, in places it's 15 miles wide and 200 feet thick of sand alone. And so that information is useful just to understand where water might be available. Maybe you don't realize your bedrock water has issues and you're treating and it's going to get more expensive. There may be one of these valleys, you know, close to you. Just, you know, talk to your resources folks is the message. Because then when you look at, this is the same map, but this is the thickness, elevation of the top of the aquifer that fills up that valley. It's all buried. And so, but it shows you where there's a lot of water available. You know, the glaciers do funny things. Some of them are thicker than others. Sometimes a second glacier will come along and scrape off a lot of that material. It just depends on how, it's just much more complicated than most folks realize. And that's why if you reach out to some of these groups like your State Geological Survey, they can explain all that to you and provide you with a lot better idea of what you're looking at for water supply and where it comes from, where it's recharged, all that sort of stuff. And then in cross section, this is what that looks like. So the deep aquifer here, the ancient Mississippi, is the Sancody Aquifer, and that's on the bottom above the bedrock. Then there's this glacial till with a big hill is actually a moraine where a glacier stopped and deposited all of its material that ground up. And that's why you have this large elevation jump, and it's mostly clay with some thin sands in the middle of it. But then the Tampico Aquifer shown here is actually part of the Mississippi after it's moved to its new location where it is today. And that's all the bottom ground for the Mississippi, and the Green River is there now, but a lot of that is sand. And that's why if you're close to a large river system, a lot of times you'll have alluvial sands, which is deposited by a river, available to you. It can be much more complicated. This is a map from an area I worked in on the Muhammad, where you can see here what we've got going on. Those squiggly lines are where soil formed. So at the bottom, above the first set of squiggly lines, or the bottom set of squiggly lines, is where the Muhammad Aquifer is. And you can see even how complicated that is. The dashed lines are lacustrine clays, which means riverbeds that are mostly silt. Then you have different sand layers. Depending on where you drill a well, you could hit 5 or 6 different sands. Now this public well that's shown here is down in the Muhammad. You can see the screen by the cross hatching on the well, but they actually went through 3 or 4 thin sands to get to that because they weren't extensive enough that they considered a water supply would be supply enough water, and they knew the Muhammad was there, which again is very thick. And so there's 3 different glaciers that came through Illinois, and after each glaciation, a soil layer formed. So the 2 squiggly lines are where the first 2 glaciers left their soil, and then the current ground surface at the top is where our current layer of soil is that was developed, which means there's trees, organic matter, and that's what the black material is here. It's organic stuff, which can certainly cause issues, and water quality if you're close to or tapping into a unit that's got an organic zone nearby. So same thing for bedrock. We have in Illinois, we have a shallow bedrock system that doesn't exist everywhere. But this is a dolomite mostly, I think. Yeah, it is. That, communities can use for water supply. And then we also have a very deep bedrock system. And I want to point out here, the blue is where we consider it an aquifer, but that deep bedrock aquifer actually exists everywhere. So that nice smooth line in the middle is because further in southern Illinois, our bedrock, deep bedrock is saline. It's saltwater, and it's from an ancient sea that was here, and so it's not potable. That line is actually moving because in the Chicago area especially, they're pumping the deep aquifer for water supply, and it's moving very slowly, but we're seeing the TDS and increasing as you move forward. And recently, a community that's very near this line decided to put in a deep well to help supplement their lake water. And honestly, it was a crapshoot whether it was going to be too high or not, if they're going to be able to treat it, because and over time, depending on what happens with pumpage further north, by lowering the water levels further north, it's making water migrate to the north. And over a long period of time, if that continues, a lot of this aquifer will be unusable or will require basically treating it like it's seawater. So this is a diagram showing the deep sandstones in the Chicago region on the right. That's Lake Michigan in the blue, and DeKalb is on the far left, and it is nearly 50 miles away. And so you can see, as I mentioned before, the geology of the bedrock isn't flat, it's usually angled. And so the recharge area is further from DeKalb, even to the left, over by Rockford, where the St. Peter gets close to the surface. So water in a natural system, if there were no pumpage, water would be flowing from left to right because the head's higher where it's recharged, and then it's lower where it's being discharged by well pumpage. But what's happened here is Chicago's grown, the Chicago metro area, and so we have Elmhurst, Geneva, Bellwood shown here. That whole area is pumping enough water that they've lowered the head in those aquifers, and this example is really for the Ironton Galesville, such that water's flowing from further right back to the left to help make that one to be level. And the red dotted line is the water level. And you can see at the industrial site in Chicago, which is right near the lake, the water levels are actually higher in the Ironton Galesville than they are at Elmhurst. And so because the water level is higher, it makes water flow based on pressure, not on what it looks like. Intuitively, you'd say, well, water's flowing downhill here towards the lake, but that is not the case because it flows based on pressure. Okay. Here's another example. The recharge area for this example, and this is right from Iowa Department of Natural Resources guidebook, it is on the upper right. So there's the aquifers are these lines that turn towards the surface. And again, because bedrock isn't flat, they outcrop in places. So here our Artesian aquifer is being recharged on the far right at the top, where infiltration's recharging it. So we expect water levels to be highest there. In this example, they made it fairly flat. That's the dashed line. And it really depends on where you're at on the landscape. So we have people all the time that think a well that's flowing is artesian. It is, but artesian doesn't mean it's flowing. So artesian means the water level in the aquifer comes up higher than the top of the aquifer. So in this unit, the artesian well that's furthest right, the water level is all the way up where the dashed line is. So it not only goes above the artesian aquifer line that's just right above the pump, but also up through the confining bed and the water table. The water level in that well is all the way up where that piezometric level. And that's because of pressure from over on the right pushing water. If I took a juice box and I put a bunch of straw in it and I squeeze it, what happens? Water comes out, or your juice comes out. And it's the same thing here. It's the pressure on the system that forces water levels up in a well. And the flowing artesian well is just lower on the landscape. And so it's flowing out of that well, causing a water level drop. So water is going to flow towards that well because it's at a lower piezometric head. And that's just because of, if they were to put more casing on that well, the flowing artesian well, and got up above that flat dash line area on the right, then that well would still be an artesian well, but it wouldn't be flowing. Because again, it's based on equal pressure. I guess the other thing here is if you have a shallow aquifer, sand and gravel, or you're in an area where it's sand near the surface and it's all water table, you can see the water table well here. The water table by definition is where is a saturation point. So above it, it's not completely saturated. The ground isn't completely saturated. And at the water table is where it is saturated. So a water table well is always going to be at the same elevation as the water table in the rest of the aquifer. So yeah, and you can see here it's discharging to a stream as well. Okay, a little bit of aquifers and Aquitards. So, aquifer is a term that gets thrown around a lot, especially like through the geologic and through all the groundwater scientists about what it really means. It really has to yield enough water for you. And so what might be an aquifer for a private well might not be an aquifer for, considered an aquifer for a community water supply because you need so much more. And it really, the best definition is saying it's, it's a saturated unit, a geologic unit that has that can produce a significant quantity or sufficient quantity of water to be a source of supply, versus an Aquitard, which really does not yield a good enough quantity of water, but it does necessarily provide leakage to an aquifer. It can, and again, it's based on pressure. So if you have a clay unit that's an Aquitard, but you have water above that in another aquifer that's at a higher elevation, it's still going to push water through that Aquitard slowly, but it kind of reaches a steady state. So there's a certain percent of recharge that comes in through that Aquitard. I know in the Mahomet, and where I'm at in Champaign County, we estimate the recharge from above to be about half to a quarter inch, and that's it. But if you move west, when you get close to the Illinois River, that same aquifer doesn't have an Aquitard above it, and it's a direct connection to the sand and gravels along the river. We get about 36 inches of rainfall in Illinois in that area, and we estimate recharge to be between 12 and 15 inches, like in the Havana lowlands in Mason County. So it really depends on your situation. And again, different users will define it in different ways. Okay, so confined versus unconfined, kind of explain that a little bit, but it's where the groundwater possesses a free surface. So unconfined means that part of the aquifer is dry, or at least it's not completely saturated. And where that saturation point is called the water table. So I already talked about that. In a confined aquifer, it means it's under pressure, like the example we showed. The entire aquifer is full. And sometimes when you pump that well, it may lower the water level, but if the water level stays above the top of the aquifer, it's still 100% full. All you've done is take pressure off the system. And how that works is by lowering the pressure in a well, you're inducing more flow toward the well because, again, how fast water moves into a well is dictated by the permeability, which is a measure of how easy it can move through the geology, and also the head difference. So by lowering the water level in the well, you're inducing more flow. And that's why a well will draw down a certain amount. And I meant to show that in that example of the Algonquin well log, because they did a pump test on it. It'll draw down to a certain point where the water going out meets the water coming in. And the amount of drawdown that takes is a factor of how good the aquifer is. So you may pump at 500 gallons a minute and it lowers your well 30 feet, and then it doesn't lower anymore because you're able to get 500 gallons a minute coming into your well because you've lowered the head enough to induce enough flow. But a confined aquifer is called an artesian aquifer, which I already described, I think. So in an unconfined aquifer, the water level is at the water table. If you have an Aquitard in between, you can have two different water levels because the Aquitard prevents flow. And so the head in the deeper aquifer here is dependent on the pressure from both sides. And this is an idealized example. And so what you've got here is your water tables at a higher level than your confined aquifer, So water is moving down through the Aquitard slowly to help recharge it because it's at a lower head. So there is water movement here, they're not at the same level. Okay, so in a confined aquifer, you can see the water table is the blue dashed line here, but the water level in the confined aquifer is below that. So as I mentioned, that means that water is flowing down through the Aquitard into the deeper aquifer. And then you can have that the other way. You know, if there's pressure from either side pushing water into the deeper aquifer at a higher pressure elevation, physimetric head, you can have a higher water level in the aquifer below the water table. And in this case, what that would mean is water is slowly going through the Aquitard on the top of the deep aquifer. It's moving upward into the water table and recharging the water table. And if it's flowing, you have a flowing artesian well. But in either case, whether it's flowing or not, it's still considered artesian. And so just to show that again, on this example, to go back through it, you can see what an artesian well is. It means the water level's under pressure. So there's water from, in this case, on the right, increasing the pressure on the artesian aquifer, causing it the water levels in the wells to go up. As far as pumping, and again, this is idealized. So if all of this was uniform sand, what you'd see when you pump your well is draw down most at the well, and then water's flowing from all around trying to fill it in. So when you look at the upper part of this diagram, that's a cross section. That's what it would look like if you could see through it from the side. And the diagram on the bottom is what the equal elevation lines look like. So you've got a cone of depression that's at 400 feet at the well, and that's elevation, mean sea level. And out where the edge is, where it's not influencing anymore, it's at 460. And so these circles correspond, if you could draw a line straight up to where it's at on that cone of depression on the diagram that's from the side, the cross section. And so that's what happens. So it's radial flow, it's coming in from everywhere because it's equal pressure, and it's trying to fill that back in. And in this case, there's 60 feet of drawdown. If this were a more permeable aquifer and it was infinite extent to the left and right, this drawdown might only be 20 or 30 feet instead of 60. And so the bottom of that would be at 430 instead of 400. And it's a factor of how good the aquifer is and how quickly water can move through it and how much water is available in the surrounding area. Okay, oh, did the wrong thing here. There we go. When you have two wells, it looks a little different. And if you're a larger system and you have multiple wells on at the same time, this is what that would look like. You know, water's trying to flow in from all around it, but in between the wells, it's competing for the same water. And so, you know, and actually this probably should have shown a little more drawdown than the 400. It's an idealized example because it's going to create a larger cone of depression because you're actually pumping more water out. And then if you're on the edge of an aquifer where there's a boundary, so, you know, I showed those river valleys and like the ancient bedrock valleys. Well, those only exist for a certain stretch of width. And if you get close to one of the edges, then there's no water on the once you get past the aquifer, then it's going to create more drawdown and take more away from in between your well and the edge, and it's going to create larger drawdowns than it will on the other side. So in this example, in our cross section at the top, on the edge of the aquifer side, you know, most of it's pretty low, and it's going to draw down a lot more, and it's going to end up using more water from the other side to fill in because it's got more water available. But you can see the amount of drawdown you have. And then on the opposite case, if you're near a river in a bottom ground, most of the time the river's connected to the aquifer directly. And so it's actually the water level in the river is the lowest elevation of the aquifer. And in this example, it's at 445. And so what you see is it's constantly recharging your aquifer, or and providing water to that well. And so you will see a narrower cone of depression and higher water levels on the left side because it's getting more of its water from the river, and it's close enough to the well. Where you could see on the other side, the natural system They're just straight lines along the river. And again, that's idealized, but that's what happens is you can draw a map of water levels and you'll see these parallel lines to a river, meaning all the water is moving towards the river and discharging there. So Mason County in Illinois is a great example of that. We've mapped those water levels and you can just see how the Illinois River, the Mackinac River, and the Sangamon River influence water levels in that entire county. So use to yield maps. So we created these maps looking by township at use to yield based on what we know about the aquifers and what the yield of those aquifers might be. And this is the shallow bedrock on the left and the deep bedrock on the right. Now, as I mentioned, a lot of communities used to use the deep bedrock, and many of them have went to Lake Michigan. But this map, I think, these were developed in the early 2000s. And so it's worse today where they're still pumping. But you can see that a lot of the available yield of the aquifers is greater than 90% for those deep aquifers. Oh, and I guess, yeah, this is labeled incorrectly. I just realized that the legend on the left map says sand and gravel aquifers, and that is not sand and gravel aquifers. Those are the bedrock, shallow bedrock. So I apologize for that. But on the deep side here, a lot of communities in the Chicago metro area went to Lake Michigan allocation because they were pumping 180 million gallons a day out of the deep bedrock, and they lowered the water levels in the deep bedrock almost 1,000 feet. So they went to Lake Michigan allocation around 2000 or around 1980, and they lowered the pumpage in the deep bedrock as low as about, I think the lowest it got to was around 42 MGD. And when that happened, we saw a resurgence of water levels and they started recovering. But over time, well, two things happened. One, all the Great Lakes states and Canadian provinces on the Great Lakes sued Illinois for taking water out of Lake Michigan. It went to the Supreme Court, and the Supreme Court capped the amount of water Illinois can take out of the lake at 3,200 CFS. 3,200 cubic feet a second is a lot of water, but it's not enough for the area. And so we've seen steadily the deep bedrock aquifer being used again, and now it's up to around, I want to say 90 or 100 million gallons a day. And so because of that, we're starting to see declines again. So as the metro area grows, it's going to become a much bigger problem. And so, looking at other aquifers like the shallow bedrock here that's listed here, or the sand and gravel, there's other issues. Like we see real salt problems in the sand and gravel because of road salt in the metro region. And so that's a water quality issue that people are going to have to deal with if they want to use that aquifer. And there just isn't an extensive shallow bedrock that's going to be able to pump a whole lot, although it's been underutilized as this map shows. And so these things are really useful to understand where the problems are in the state, where if we're dealing with a particular community, where we might consider looking for additional water supply. And so having these this kind of information is a great resource for you, especially as you plan for additional use, like if your town or your community is growing, or you have a big industrial user that might want to come into the area. So I mentioned road salt. These are chloride values. There's 3 different maps here. You can see let's start on the right. That's the deep bedrock that's shown in the gray and that familiar smooth line. You can see as you move south, the amount of chloride grows to over 500 in some places. And because of that, we're seeing it migrate and that line is moving up. But up in the Chicago region or in very northern Illinois, even in the Northwest, it's mostly low. And there's one anomaly there. I'm not sure what that's from, to be honest. But we see that's a natural system. There's water replenishing part of that bedrock that's high in chlorides. And so it's causing an issue. And that's why when you get where the chlorides get to be over 100 or 200 or 250, I'd say, we don't see a lot of communities using that aquifer anymore, other than, so it's further north where most of the pumpage is. In the middle one here, those are actually sand and gravel aquifers in the light blue. And you can see it's kind of a mix. It's all over the map. And that's what you'd expect. Some of them are based on upwelling of bedrock. I know in the Mahomet, we have an area where there is bedrock water upwelling into the sand and gravel Mahomet, and there's chloride values near 500. and that's in DeWitt County, which is just next to Champaign County. But in general, there's a reason. It's usually because there's a connection to the bedrock or something like that. But then on the far left here are surface water supplies, or not supplies, surface water samples. And it's pretty obvious what's happened here. So this is actual surface water chloride values. You don't expect to see chloride values of 100 milligrams per liter in a river. Yet that's what we're seeing now in the metro region, and all because of all the salt that's used in the winters. And so it's a real problem, and it's changing the ecology of some of the lakes, as well as something you might need to deal with if you're pulling from one of these rivers for your water supply. And this is just some of the towns up there, communities up there. And you can see over time how these are shallow sand and gravel wells. And you can see how in some places they've really increased a lot in chloride because of road salt. And that just, it's surface infiltration. The shallow sands and gravels are close. But the whole point of showing all this is that no matter what state you're in, your state resource agencies probably have some of this data, or your USGS may have done some of this type of work. And so it's worth exploring and understanding what the situation is for you, in addition to any compliance sampling you've done for that. So that's what I wanted to talk about today related to geology and wells. I do want to talk a little bit about wateroperator.org if you're not familiar, and just give you some examples. And so this website is funded through RCAP and the Rural Community Assistance Partnership through EPA. So it's EPA money, and it allows us to offer for free a lot of resources to water and wastewater operators. And so we have a calendar that we put about 15,000 events a year in. That's every training event for water and wastewater operators in every state. And it's meant to be a resource. And so there's also 15 to 16,000 resources that we've vetted. So there's no fluff, there's no advertisements, there's no anybody trying to sell you anything. It's just information from groups like WEF, AWA, state sections, TA providers like Rural Water and RCAP, EFCs, USDA, EPA. It's all the sources of, and it's all free. So anything in here is freely available online, and we actually just link to it and try to provide it and make it easy to find. So I'm just going to show you quickly how to do that as we go through this. So it's a clearinghouse, as I sort of mentioned, of information for water and wastewater operators. And again, it's all free to you. And you can even contact us and we'll look for stuff for you. And we've done a lot of legwork to make it easy to use and add value. It's like we provide summaries of documents so you don't have to scroll through 50 of them to find the one you're interested in, for instance. And so we actually brought in some small community operators in Illinois to work on this. We set them around a giant table and gave them lunch and asked them to go through this and tell us what they liked and didn't like when we first started this, which was like in 2009. And so it's easy to use once you understand it, and it should be something you use anytime you're looking for information, or if you're trying to find a class to take, that sort of stuff. And again, you can call us, you can email us. On our webpage, there's a phone number and a email address, and we're glad to try to help find information for you or steer you to a person in your state that can help you if you have a question that's beyond what might be available in a document. So we have about 800 organizations that we go to regularly on the web, and I have 5 staff that do nothing but find that information, add it into our database, and make it available. This says 13,000 events. It's probably closer to 15,000 a year. But it's everything going on in your state. And we also work with your state primacy agencies to make sure we're covering our bases and we have everything involved. We regularly, or every once in a while, get a call from a state primacy agency saying, hey, you don't have these events on your web page. Could you make sure they're on there? Because they direct operators to us as well. So it's like I said, value added information. It's meant to provide, we write a summary of every document. So my staff actually go through and look at a document, write a summary of what's there, and then when you look through that, you can just look at the summary, which is usually 3 or 4 sentences, so that you can know if that's really what you're looking for, you can move on. And yeah, so I'm just going to show you a couple examples. First, the calendar. So on this page, there's an event calendar at the menu on the top, or you can say search the calendar on the bottom left. So if we go to that page, it lists our trainings like the one today. This is an old slide. I didn't change this one. It doesn't have today's event. Oh yeah, it does. September 10th. Sorry. But if you go to our calendar and select, if you click on the select button, if I go back here at the bottom here, you see it says select. When you click on that, it gives you a choice of state, type, organization, or category. And so most of the time, if you're looking for events, you're going to look in your state. We have all 50 states. Everything is there. So when I select Illinois, it shows me all the training going on in Illinois. Right now, it's dominated by Illinois section, but also certification classes from Illinois EPA. They do their own. Other groups like BHC is on the 24th. That's Blackhawk College. And JJC is Joliet Junior College. And they have classes for operators as well. And on the 9th, it says Illinois Rural Water. They usually have a lot of classes as well. So if I want to narrow that down, and I know I'm not going to go to an in-person training, which in Illinois they've started. Some of these folks have started doing in-person trainings again. But you can say type webinar or online, and it's just showing you the webinars that are available or live online. And so if I select one of those, Illinois Section Lead Service Line Replacement Case Study, it pops up a window that shows me all the details. It's $30 if you're a member, or it's free if you're a member. It's $30 if you're not a member. It's worth 1 credit. There's the contact. You can click on that link for event info, and it'll take you to their page with all the details where you can sign up. And we put this information in a database for every single event you find on our calendar. So you can find out who it is. It takes you back to their site. So in essence, our job is to help you find stuff at Illinois Rural Water, Illinois Section AWA, RCAP, every TA provider that's doing training. Our job is to help you find that in an easy way. So we include all the training from all of these providers in one place. So as another, if I just say webinar, I showed this because this is from the April event calendar. So I clicked on type equal webinar with nothing else, no state, no nothing. And you can see the number of events here. Well, this is right at the beginning of when things went south with COVID. And so a lot of organizations didn't do any online training. And so they're still coping with how to find it. So nationwide, this is all the training that was available online as a webinar. Some groups have been in that business for a while. You can see the ones that keep showing up. Turns out Illinois Section AWA has always done online training. So is RCAC, the Rural Community Assistance Corporation. That's the Western RCAP. And so you see a lot of events from them. But this is today. This is only the first 5 days of the month because this thing goes down for about 5 pages. So everybody's gotten in the game. I mean, really, there was no choice, right? If you're going to get your CEUs, everyone had to figure out how to start doing online training. And fortunately for operators, and again, this is water and wastewater, this is a kind of, what's the right word? Intimidating just to see this list. So what we would recommend, if you look at our calendar today, is search by your state, because what that means is it's likely we're CEUs in your state. Or you can also search by topic. So when I said webinars online and groundwater, added that as a category, now these are the events that show up. TEACS and Texas Rural Water in Texas. TECEQ is the primacy agency in Texas. But you can see there's different groups here, including our webinar. It says WOO 2023 webinar series. I need to talk to my staff because WOO is a term we use internally, meaning wateroperator.org, but it's not something that people recognize, and we probably shouldn't have that on there. But this particular webinar is listed as well. So I clicked on the Illinois, or the American Groundwater Trust Missouri PFAS webinar, and it pulls up those details. This costs $200. You can look at what it is. You can go to their webpage and read more about the event if it's something you're interested in. But again, any event that's worth, and this says credit approval requested from Missouri. So it actually hasn't been approved yet. And I know for most of us, if you're going to attend a training like that and spend $200, you want credit for it as well. So that's something to find out before that occurs. Okay. You can also look for things that aren't in our category list. I'll explain our category list in a minute. There's 32 categories, and we've broken that up. It's mostly because of the documents. But when you're searching on the event calendar, most of the time folks are searching by state. And so the calendar topic isn't as relevant. Usually it's easy enough to read right from the title. But for instance, if you want to look for COVID, there's a keyword search on the upper right. So I typed in COVID, and you can type in any topic there and it'll try to match it. And so here's what's come up for COVID related webinars. And the thing is, even if it's not worth CEUs for you, like if you decide to go to the RCAC co-op thing that's for Colorado, you're gonna, if you're really trying to learn something about a topic, you know, many of these are free. And then you can look and see. I didn't click on any of these, but a lot of these are free. You know, and Massachusetts does a lot of work. The EFCN is doing something there, but that's probably being paid for by their DEP in Massachusetts. And so that's likely free. And so it's a way you can learn about topics that you're not familiar with, you know, and that runs a gamut of things like, you know, maybe you have chlorine issues because of disinfection byproducts and you're trying to consider UV. You can put UV up there as a topic and find information or in a class you can attend related to UV, things like that. So if you click on Resource Library in the upper menu across the top on whatever page you're on, it brings up this page. And the other thing is the document search. You can also get to document search from the home page. But if you click on document search, it's set up the same way, except what it's going to retrieve are documents related to those topics. So most of the time, if you're looking for a brochure, a handout, a manual, or whatever, or a web page, you're going to search by category because you're trying to find something on a specific topic. So what we've done, the search criteria, again, it's category, type, state, or host. And type, you can see the list there, manuals, newsletters, slides, videos, or even CDs and programs and spreadsheets that you can download. But category is all the topics that relate to water and wastewater. Some are specific, like lead and copper, and some are more general. These are the topics we have that are really related to either water or wastewater, and these are the ones that really, it doesn't matter whether you're a wastewater or water operator, certification information, consumer information, financial management, all that sort of stuff is really useful to you. And so you can select any one of these categories when you're going through this filter. So you click on the select button and then click on category, and I selected arsenic. So it shows that there are 187 records related to arsenic, and there's 19 pages of 10 here. So what I want to show you is the title is in blue because if you click on it, it'll take you directly to that document. It gives you a summary. There's a short summary and then a long summary. The second one, number 2 here, it's a summary of what that entire document's about. You know, number 3 is about absorption technologies related to arsenic. And so it's a slide presentation from US EPA. So you can quickly scroll through this and read what you might be interested in downloading rather than an advanced downloading, especially some EPA manual that's 400 pages that might, you know, you have to look through it for 20 minutes before you decide what you want. We've gone through and done that for you. And so, and again, these are all vetted sources, which means they're only groups that are either state agencies or actual TA providers or associations, or federal agencies or state agencies, but we list all of their stuff in one place. And, you know, I don't want to pick on the EPA, but trying to find information on their website sometimes is a real hassle. There's pages that we link to that we've discovered now aren't linked to anymore through a hierarchy. So you can't even get to the page where this document is unless you already know the URL. And so, you know, we're trying to make that easy for you all. And so in Illinois, we know iron removal helps with arsenic removal. A lot of our plants in Illinois are water plants that have arsenic problems are also removing iron. And in some cases, they're able to optimize, even add iron before they take it out, so it'll remove more arsenic. And so if you wanted to look at information on that particular topic, you can look, and I've added iron here, and there's 34 records. As I scroll through those, one of these is a presentation from EPA called Arsenic Removal During Iron Removal. It's exactly what I was looking for. And so when I click on that, it takes me to this presentation. It's by Darren Lytle. He's at ORD, the Office of Research and Development, and one of the foremost experts on arsenic in the country. So that's really cool. For one thing, that this is available, but it walks you through. And as you go through the slide deck, you run into this actual case study from Michigan, where they're trying to remove iron and arsenic, and it also removes manganese, and so which has become a big issue today. So when you look at their plant they're using, they decided to test what happens when they add chlorine. When they add it at the end, they get 50% arsenic removal. When they add it in front of the pressure filters, they're still getting 50% arsenic removal. But when they added the same chlorine at the same rate ahead of their treatment plant, after the wells, now they're getting 75% arsenic removal by doing nothing different except putting it in the system in a different place. And so, that may save you a ton of effort, or even having to add treatment to your system that might be really expensive. And it's an example of just the type of material that's available. And so I won't go through any more of those for brevity, but you can search for anything. And I'm always willing, if you give me a call, to hop on my computer while you're on your computer, and we can walk through trying to find stuff. I do that for a lot of operators, and be glad to. So you can always consider that if you get lost on the site, or you can't find something you're looking for. It may be that we don't have it, but what we'll do for you in that case is we'll try to find it, or talk to someone who may have it and see about getting you the right materials. We also have a class that's for CEUs. I think we're up to maybe 24 states that accept online classes, our class for CEUs. But when you click on that, it takes you to this groundwater and well care for public water systems. It's a 6-lesson class that's based honestly on our private well program. That we have a 10-lesson class for private well owners. But in this case, we went to the effort. If you're ever dealt with trying to get a class approved for credit, you know what a burden that can be depending on the state. That's why after 3 years of having this class available, we only have 24 states that accept it. Some just, and some of those states are changing now because of COVID, but there are a number of states that just do not accept online training. And I understand their logic for that. And so you need to check, there's a list. I think as I go through this, there's a button you can click on the course overview that tells you whether you can get credit in your state and what the rules are. Because they're different in every state. Some states require us to keep records for 5 years. Some states require us to have them to send in something after every month, that who's taking it from their state, all that sort of stuff. And so it really depends. And like here it says Georgia and North Dakota only accept it for 1 continuing education credit. So they went through the class and decided it's really only worth 1 hour. But still, that's a free hour of credit for you if you're in one of those states. Again, this is all free. Everything that we do is publicly available and free for operators. So this is just what it looks like. It walks you through the hydrologic cycle, some of the things we covered today, but there's a lot more detail. And you have to pass a quiz at the end of each chapter. And that's part of making it worthwhile and making sure you actually go through the videos and everything else. So once you're done and you've gone through the class and you've taken the quizzes, I took it and I got 100%. What a surprise. But then you can get a certificate for that and turn it into primacy agency, or in some cases we have to turn it in for you, depending on the state. And so then it's the only class we have. Our job isn't to compete with all the TA providers out there that do training. We don't want to do that. We want to actually help you find those TA providers and the classes they provide. That's what they do for a living. We just have this one class that actually started out, and this is an old slide because it still says non-community public water systems. We were asked to provide a class for non-community water supplies. And in doing that, after we built it, we found that a lot of community water supplies were also interested, and a lot of states wanted us to make it approvable for both. And so now it's just groundwater and well care for public water, or for community, for public water systems, I believe is the way it's titled. So yeah, and that's the only class we offer. And yeah, I want to tell you about our newsletter. It comes out every 2 weeks. There's no fluff in it. It's steadily grown since we started it. We started with about 100 people on it in 2009 or 10, and it's up well over 2,000 people. A lot of those are operators, but also TA providers and agencies. We try to provide the best information that'll help you with today's issues, common sense things. We highlight a document and a video. There's a lot of great videos out there that other folks have done on, one of the Chicago area communities, one of the suburbs, has a great video on how to fix a water main break. And it's really they put it on YouTube for their own staff but it's actually a really cool thing that anybody can use. A lot of useful stuff, and we highlight that in our newsletter. If you're interested, you can go to our website. There's a newsletter tab, and you go there and you sign up, and just with your, I think, first name, state, and email address, and that's just so we can show that we have people from all 50 states who use our newsletter. Or you can even text tap water to 444-999. One of my younger staff took care of that, I guess. And you can sign up that way. And it, like I said, it comes every 2 weeks. It's an email, so it's self-reliant on you if you want to look at it or not. But it's a lot of useful information. A lot of folks really give us a lot of compliments on what's available there, and we stay on top of the game so that we can help you find that information. So we're at the question stage of our webinar, and a number of you submitted questions. We're going to try to answer many of those. We can't answer all of them, but especially if you just signed up in the last day or two, we probably, I did not get to those. But Jennifer's also available. She's on the line, and if you want to put a question in your question box or chat box on your GoToWebinar panel, she's going to make a list of those. And if anything I said today, but if you asked a question in advance, it may be covered here, so you should see if that's where we go. And Dick, are you on the line?
There we go. Can you hear me now?
I can. Yeah, you sound a little distant, but I can certainly hear you. So fortunately, great. So fortunately, we have Dick Meiliger from Municipal Well and Pump. It's interesting because I'm more of a private well person, and I understand a lot about those issues. But some of the questions we got in our April webinar from you all about more on operations side for large wells and some of the other issues you might have, I was outgunned, and I knew I was needed some help. So I contacted Dick. We know each other from both from Illinois Section AWA work, and just that they've been around forever doing wells in Illinois, municipal wells. And he's graciously been helpful of both webinars, providing much better quality answers than I would have been able to give you. And so I'm going to read these questions, and Dick's going to answer them, basically, is what we're doing. And he provided the answers in advance, and I put those on the screen. So these will be part of the slide deck. And if you want a PDF of all the slides at the end, you just need to email us and ask for it. Okay? And so I need to fix this. Okay, there we go. So the first question was about pumping sand. How much sand should a well in good shape produce? Dick?
All right. Well, there's usually I like to have less than 1 part per million for food processing, 5 parts per million for homes and municipal systems and supplies and industries. That's actual published numbers. Groundwater and Wells, book by Johnson Screen, has some additional information. Obviously, you want as little amount of sand as possible, but that's not always the case.
Yeah, so, it's not unusual to pump sand, is the bottom line, a little bit. But when you start seeing a significant amount of sand, that usually means there's a problem, like a breach in your screen, right, or something like that.
Yeah, one of the things we've seen with the decline in water levels drastically is you are reducing the water pressure on the formation, and wells that were not sand pumpers in the past have now become sand pumpers due to the reduction in pressure. So that's something that we're always worried about too, especially now in the Joliet area where the Ironton-Galesville water levels are declining quite rapidly.
Oh, sure. That makes sense. Okay, wire to water efficiency. And I'm glad you explained this, and this is on 2 slides, because I had no idea what this was. So I really appreciate, what's the acceptable range of wire to water efficiency for a well? What's the highest efficiency we should expect after well rehab?
Well, wire to water efficiency is an actual electrical measurement. So you're looking at the efficiency of your pump and the efficiency of your motor. You combine those 2 efficiencies with your production to get a wire to water efficiency. Obviously, you want to maximize that. There is no magic number, but sometimes in bid specifications, they will want you to meet a certain number. And sometimes if you exceed that number, you'll get penalized. And if you do better and get a higher wire to water efficiency, you can be rewarded. As far as efficiency in wells, typically I think what they might be thinking of is a sand and gravel well, where you're looking at what you talked about in the beginning of permeability of formations. You can look at the production of a sand and gravel well, but in order to come and arrive at an efficiency of that well, you need to have a piezometer located so many feet from your production well so that you can measure water levels in your piezometer well plus your production well and go through a very strenuous.
Uh-oh. Dick, we lost you. Now we got you.
Are you there?
Yeah.
Okay.
Strenuous was the last word we heard.
In order to get efficiency of a well, it's typically in a sand and gravel well where you measure the water level in a piezometer well located maybe 50 or 100 feet from your production well, and through a strenuous calculation of the water level in your piezometer and the water level in your production well with gallons per minute, you can come up with a well efficiency. So I'm not sure what the question was addressing, whether it was a well efficiency or an electrical efficiency, but I think I addressed both. If someone wants a little bit more detail, feel free to contact me.
Yeah. You should have included that. Thank you. What does it mean to sleeve a casing when it's corroded?
Sometimes we run into older wells that have the steel has become corroded. Sometimes holes develop. You can sometimes pump sand or material through those holes, or undesirable water quality from a higher level. You can do one of two things. We'll address a corrugated sleeve, I think, in the next couple of questions, but I think what they're getting at here is, say you have a 12-inch diameter well that has corroded casing, you can put in a 8-inch diameter inside of the 12, past the area of compromise, and then fill that annular space with concrete, neat cement, in order to seal off the corroded part of the casing.
Yeah, I think that part of that is also another question we got, and I included both of them. And so the other one was about recasing a well, I think, and it might be the next question.
Yeah, I probably put the cart before the horse.
Oh, no, it's all good. Yeah, but it's the same. In this case, though, what you're talking about is an entire casing all the way down, not just a section to help with the corroded part.
Correct.
Right. So, yeah, and you made a good point here at the end. When you do that, it may mean that if your existing pump or anything you have down your well needs to fit in that 8-inch pipe instead of 12-inch. So, okay. If a water system is transitioning from groundwater only to source, that's supposed to say source water. Well, for groundwater only source to adding surface water treatment, what are the main considerations for safe delivery of drinking water? And that kind of changed your answer here a little bit.
Good.
Well,
I'm glad you did.
Well, what you said here was, what you had said is about, that's a legal issue, and it really is. It's if you're going to mix those waters, especially, I'm sure your state primacy is involved anyway, because if you're going to change your treatment, you have to get approval, at least in most states you would, in order to do that. So really, you need to talk to your primacy agency about making sure you run your system in a safe way. But what we've seen is examples in the past of where a community had either groundwater and they wanted to supplement an aquifer and add surface water into the groundwater, or they've got actually two systems and they're blending. And if they're not careful and they haven't looked at the chemistry, you can have unintended consequences is the bottom line, and so you need to make sure that those two chemistries will work together. And I know there's cases in the past around the country where it's caused contamination of the water because the chemistry was different and the way it reacted. The surface water is certainly different than groundwater in how oxidized it is and a bunch of other things. So what you said about cross-contamination and backflow is certainly correct there. But you need to make sure you've looked at all that and how the water is going to work together. And I don't know that I've ran across a system where they can run either surface water or groundwater, but not both, because I don't know how you get it in your distribution system separately. And so there's going to be issues with that water mixing, and that's what you really need to be aware of and have tested through and understand. Okay, so what aspects of well care is the state regulating for responsible for? Go ahead, Dick.
Well, a good question. Obviously, you got to.
Yeah, we lost you.
Through your equipment and good. Yeah, I'm losing my connection every once in a while. I apologize. But that not only includes your well and your pump, maintaining that in a good working condition, but your distribution system, your pump house, your pressure tank, distribution system, etc. Some of your sanitary requirements might be a good place to start.
Yeah, so a sanitary survey is a requirement for public water supplies every 3 years. And what I noticed, Wyoming doesn't have primacy. So the US EPA, Region 8, I think, is the primacy agency for Wyoming. And what we found on their website, well, many moons ago, was a actual blank sanitary survey, the one they used there. And I know it had a lot of questions about the well and that side of the system. And so if you're a groundwater supply, I'm guessing if there's anything wrong or concerning with your groundwater system, including all the things Dick just mentioned, your pump house, pressure tank, all that stuff, as well as through your treatment plant, they probably listed those there, and it's probably worth taking a look at what that has to say. So, okay. So what's different about a well cap that is flood proof versus a regular well cap? I learned something new today.
Well, a regular well cap or a discharge head of a pump is going to have a vent, because you've got to allow for when you pump your well and you get your water level dropping, you've got to allow air to enter the well, and when the pump stops and your water level recovers, it's got to go back, so it's got to be vented. A true flood proof cap would not have a vent on it, because you want it to be watertight, airtight in case of any flooding. What we typically do in a flood situation where wells are located on or near a river susceptible to flooding is we actually raise the casing of the well up higher. As an example, LaSalle area where the wells are located right on the river, the wells are extended up somewhere between 20 and 30 feet above the level to accommodate that.
Yeah, it's really interesting to see, a well house up on top of a casing with a ladder that goes up 20 or so feet. And you mentioned that you have to at least extend the vent above that. And I don't know that I've ever seen that. It's always that the entire well is up that high. So
right, that's yeah. typically what you run into.
Yeah. Okay. Okay, so hang on, because we need to see if there are any other questions. And so I'm going to pull up. I'm going to make this a little larger so everybody can read them. Hang on. Nope, that's too big. I can't read that myself. Okay, so first question. So recently we had a special sample taken from a well house and found nitrates in our system. Do you recommend drilling a new well and at a new depth? Wow. Dick, what's your take on that? You want me to go first?
Yeah, you go first. I'm thinking how to not get complicated in my response. So go
Yeah,
ahead.
no doubt. Well, so a nitrate sample likely means that the aquifer does have nitrate in it, obviously. There's several options. One would be to treat it instead of trying to drill a new well. It really, when you get to the point of asking, do you need a new well or at what depth, that's a site-specific question. And it really depends on what your situation is. And nitrates, we do see, so some of the research we've done in areas where there's especially shallow aquifers, we do see a profile for nitrate. It's higher near the top, it's lower down deep. Sand's a natural filter. We have a couple aquifers in Illinois along like the Illinois River where, it's 100 feet of sand. And if we took a sample every 10 feet of depth, if we could do that, we'd see nitrate at the very bottom of that aquifer lower than it would be at the top. The problem is once you're pumping a community well, you're pumping a lot of water. You could be lowering the water level enough that it's influencing that shallower water getting into your well and moving down through that unit. So that's all I know without having more details. Because
Steve,
yeah, go ahead.
Sometimes, again, site specific, depending upon your well construction, we've done a few where we'll go in and conduct a packer test where we put a pump in with an inflatable packer, almost like an inner tube on a tire, and seal off. Say if your casing goes down to 100 feet and your well's 200 feet deep, you've got 100 feet of formation to work with. We'll go in and put a packer in at 125 or 150 and then pump the well and see if we can reduce the nitrates that way. Then put the liner in like we talked about before, where we seal off a portion of the well, in this case sealing off the nitrates. Not always possible, but it could happen.
Yeah, that sounds like a great idea as the next step, actually. If you can figure out where it is, because then you could just
right.
You could seal that part off. Isn't it in Wisconsin where they have a unit that you can't put a well in because of arsenic?
There are some areas where you have to construct the well differently. We also have to modify our drilling methods. We can't use air when we're drilling because getting oxygen in promotes increased levels. So you have to be very careful in certain areas and drill to certain depths so that you get past the bad geologic areas.
Right. All right, great. Thanks. So for the next question, how many publications are in your resource database? So Jennifer filled that in with 15,392. There's a quick cheat way to find that out. If you go to the documents and don't select any of the category type, whatever, but just go over to the keyword search and put in the letter A. Every one of our summaries and titles and all that stuff are going to have an A in it. And it's a good way to quickly see how many documents there are. And we recently, my staff have went through and taken out older documents or where there might be a newer version. And that number used to be closer to 18,000. But some of those were put in 2009 or 10, and they're either not relevant or they're not, don't fit as well today. And so we've removed some of those, or we're just, better at deciding what we should keep. It's not like you have to search through 15,000 documents, though. You can narrow that down like I did just by using a few keywords to get that down to a manageable number. So next question, I was wondering, how do you collect information about training across the country? So, well, we work with all the primacy agencies. We've contacted them when we first started, but we also have identified all the trainers that are in the country in every state, and we create a big list. We contacted them, told them we were going to do this. Most have been very receptive. The one thing that sometimes we might miss are trainers that don't have websites. And so what we've done there, every once, probably once or twice a year, we have someone contact us and say, hey, I've got training and I don't have a website, or I'm not on your list. How do I get my stuff on your website? And so we explained to them it's either got to be free or it's got to be worth CEUs for us to list it. So if there's free training, even if it's not worth CEUs, but it's on a wastewater or water topic, we're going to share it because it's something that you can, it's just your time if you're interested. And that doesn't necessarily go for companies. We've tried to be really careful about not, if somebody's trying to sell their product and they're doing a webinar that's just about their product, we don't list it. It's got to be about that method or that approach or that type of, it can't be specific about a product. Just because we're not trying to help somebody make money, we're trying to help operators find information about what their options are on different topics. So hopefully that answers your question. If you have a trainer, I early on I ran across a trainer in one state who had a really nice business set up, and he did everything by email and didn't have a website. We found out about his training. I reached out to him. He did not want to share his information with us. And my own take on that was that he probably charged more than some of his competitors, but he had a great clientele set up. So that's what he chose to do. And we honored that, and we don't list him. I've never talked to him again. But it's a disservice to all the operators he serves not to share that information and not to be competitive if he's an independent trainer, which he was. So that's what I'll say there. But anyone's welcome to contact us. We have some states who, instead of maintaining their own calendar now, just have them come to ours. And so it's really worth your time. And if you know of an operator or a trainer who's doing good training and they're not on our list, have them contact us. We'll certainly add them as long as we're CEUs or what they're doing is free. So last question. In general, should we monitor the water quality of karstic and fractured aquifers more frequently than of our porous aquifers, as karstic and fractured ones do not have enough, quote, natural filter character, end quote, like that of porous aquifers? If you're a community water supply, then you need to follow the guidelines that are set up for your state as far as sampling. Because in all likelihood, if you're sampling every 3 months, you can certainly have a big rainfall event that changes the water quality in a karst aquifer right away. And that might be a good best practice for doing your due diligence to protect your customers. But it's certainly, it's not required. And I would say it's an individual decision for a community. The best example I can give is Pike County in Illinois. Based on their private wells and its karst, their community or their county health department sees about 80% of the samples that come in from private wells as having E. coli. And that's not changed. And that's just because of the nature of karst topography and sinkholes and how connected it is to the surface. And so, so one of the things that I've done is I've helped a few with a few grants where they've reached out to USDA to try to build a rural water district in those areas. And I wrote letters of support talking about the poor water quality and the how much expense it would be for a private well owner to have their own treatment to take care of that. And so in some of those areas in Pike County, they now have rural water districts that are basically a large community water supply. So I'd say if you're in one of those areas, you're already in that game, or you should be, and understand what those problems typically are. And it's likely you're treating it as a surface water supply to begin with. And if that's the case, then you should be covered there. If not, I'd reach out to your state agency. I can't believe that you haven't already dealt with that. But anytime it's under, there's a term for it, groundwater under the influence, and especially a lot of wells along rivers may have to treat like surface water in the first place. And I would say that that's what you'd want to do if you're in a karst situation, is to add tertiary treatment and make sure that you're doing all that. Dick, anything to add?
No, I would have said all you just said in the less amount of time and not as descriptive. So you did a nice job.
Thank you. All right, well, that's all the questions we have. I appreciate everyone who stuck around. And Dick, thanks again for all your help and
You're
being
welcome.
here today. And yeah, I really appreciate it. And if you have any further questions, I think further down here, I've got our, yeah, there it is. Our email address is info@wateroperator.org, and let us know. So appreciate your time. When I end the webinar, Dick, it ends it for everybody, so we're going to get cut off.
All right.
Thanks again, and appreciate
You're
your
welcome.
time.
Thank you.
All right, take care. Thank you,
Bye, guys.
everybody.
Bye.
Have a great day.